We say that two different experiments are independent if the outcome of one experiment does not affect the outcome of the other. For example, if you and I each flipped a coin at the same time, the result of my flip has no effect on the result of your flip. These are independent. On the other hand, if I were to roll a dice and then flip a coin that many times, the second experiment depends on the outcome of the first, so these are not independent. When we combine two experiments, we talk about their joint probability. And if the two events are independent, then we can compute the joint probability by multiplying the probability of each individual event. Let's start with an example of independent events. Let's suppose that you flip a fair coin. The sample space is either H for heads or T for tails, and the probability of each event is exactly 1/2. For the second experiment, let's roll a weighted dice. The sample space consists of the face values 1 through 6, and we favor the roll on odd numbers over even numbers like so. To warm us up, let's compute the probabilities of a heads with a 5 and a heads with a 6. Then we'll look at the probability of a heads with an even number in general. While not necessary to the problem, let's think about the joint experiment. The joint space has 12 elements in it by the basic counting principle. There are 2 possibilities for the coin flip and 6 for the dice roll, and we can roughly write them out as follows. Now, these events are independent, right? The dice roll is not affected by the coin flip and vice versa. So when we compute the joint probability, we just compute the probability of each event separately and multiply them together. With the roll of heads, we get 1/8, while with tails, we get 1/24. If we think about this, it's not surprising. The probability of rolling a 5 is 3 times more than that of a 6. And since the events are independent and both have the same coin flip, we expect this should be true in the joint probability as well. If we move our attention to the prescribed event, it consists of 3 elements, all of which have the exact same probability. And we've already computed the probability of heads with a 6, so the probability of the event E is just 3 times that, or we can work that out to get it 1/8. Let's give an example of a non-independent experiment as well, just to clarify our definition. Let's suppose that we have 2 black and 2 white balls in a bag. I'm going to pick 2 balls from the bag without any replacement. What's the probability that I pick 2 balls of the exact same color? Let's think of each draw as its own experiment. Since we're not replacing the ball after drawing it, the probabilities of the second draw are affected by the first draw. So these experiments are not independent. If we label the draws as A and B, they have the same set of possible outcomes, either black K or white W. Let's break this into 2 cases and look at the probability first of drawing 2 black balls. In the first draw, there are 2 white and 2 black balls. We're going to pick a black ball to start. Now this leaves us with 2 white and 1 black ball in the second draw, wherein we also want to choose a black ball. So in the first draw, there's a 50-50 chance of picking a black ball, but there's only a 1 in 3 chance of choosing a black ball in the second draw. Thus, the probability of choosing 2 black balls works out to be 1/6. The other case of 2 white balls is exactly the same as 2 black balls, which we can just read off as 1/6. Thus, if E is the event that both balls are the same color, the probability is the sum of these 2, or that works out to be 1/3.